So today's panel topic is how can we improve clouds in the models. So our Dr. Hugh Morrison from NCAR is the chair of this session. First of all, I want to welcome all of you to this session, and there are quite a few eminent panelists in this session. Jason Milbrandt, Environment Canada, Lulin, NCAR, Wojtek Grabowski, he's not here, but he's in the panel. Adele, Igel, University of California, Davis, and Axel Seifert, Deutsche Wettedienst, Germany, Paul Field, UK Met Office, Kali Furtado, UK Met Office, Corina Hus, Karlsruhe Institute of Technology, Germany, and Sue Vandenhever, Colorado State University. So these are the names I have in the panel, and I want to welcome all of you to the panel, and please, I also would like to make another announcement that we have a problem in Gather. It is not a problem rather, but in this particular room, you see that you are all able to communicate to each other. So the panelists I am broadcasting to the entire room. So we can have only a capacity of maximum 100 people in this room. So we have made a provision for broadcasting to another room in the backside, where we are doing a YouTube live telecast there. So I would request, when the number is exceeding, today definitely we will get more than 100 people. So I would request volunteers to go to the backside room. It is also a similar room only. Whenever you want to have a discussion, you are free to come inside this room and have the discussion. It is just to have a very seamless conversation. We have to do this. Only those who are wanting to have interactions be in this particular room. So those who are sitting here, I would request them to come to the red chair at some point of time. That means, okay. Thank you, Hugh. Now I turn it over to you. Thank you.
Okay, thank you, Tara. So we'll go ahead and start, and we had some last-minute kind of shuffles on the panel. So I'm glad to see Corinna here as well. So I think first we'll maybe just briefly go through the panel and maybe just quick introductions and sort of, say what you're working on related to this topic, and maybe like any other statements you want to make on that. And then I have about 5 minutes of material just to set the stage, and then we'll just open it up for, really a general discussion. I don't want to keep it really, focused ahead of time. We'll just sort of see where the discussion goes and take some questions from the audience as well. So let's go ahead and start. I don't know, we'll go maybe left to right on my screen. Paul, do you want to say something?
Okay, yeah, so I'm Paul Field. I'm at the UK Met Office, and we're basically trying to work on putting in a double moment microphysics into the operational model. Is that all you wanted from me initially?
Sure. Yeah. Okay, Corinna.
Yeah, hi, Corinna Hose, Karlsruhe Institute of Technology. I'm working on modeling clouds at different scales, and I'm particularly interested in processes in mixed-phase clouds, primary and secondary ice nucleation, where I think there's still a lot of puzzles to solve, and laboratory experiments and field observations are telling us new things every couple of years, and we're trying to represent that in the model.
Okay, thanks. Lulin?
Lulin Xie from NCAR Research Application Laboratory. Work on cloud microphysics and modeling side, and also using bulk and beam microphysics, and recently also work with our colleague CC Chen using DNS and particle-based microphysical representation to look at how we actually can represent clouds in model in a better sense. Thanks.
Axel?
Okay, yeah, Axel Seifert from Deutscher Wetterdienst, so the German National Weather Service. And obviously, I'm also working on numerical weather prediction, a little bit like Paul, putting two-moment microphysics in operations and so on, data assimilation stuff with clouds. But on the research side, we are doing Lagrangian particles for ice microphysics. Precipitating boundary layer clouds is a topic I worked a lot on. And recently also multi-frequency, polarimetric radar data for model validation, which I think is a really important topic.
Thanks. Adele?
Hi, I'm Adele Igel at University of California, Davis. I work on, like everyone else, cloud microphysics. I've simulated everything from fog to mixed phase clouds and deep convection, and thought about bulk schemes in particular. I've done a lot of work on representing the size distribution bulk schemes, and then most recently I've been developing a new hybrid bin bulk scheme to answer questions about limitations of bulk schemes and ideas about ways to improve them.
Thanks. Jason?
Yeah, hi, I'm Jason Milbrandt. I work for the Meteorological Research Division at Environment Canada. We work fairly closely with the operational NWP part of that department to build the NWP models, the operational models. So my focus has been on maintaining and expanding the bulk microphysics for the kilometer scale models. So more recently, I've been focusing on continued development of our P3 microphysics scheme and generalizing that so that it's more useful on a broad range of spatial scales. So the plan in Environment Canada is to have that scheme in most of our NWP systems.
Okay, thanks. And I guess I'll go last. So I'm Hugh Morrison, and I work on I guess a mix and match of different microphysical modeling activities. Lately, I've been focused a bit more on bring in some statistical elements to bulk microphysics modeling, as well as on the research side, Lagrangian particle modeling with our postdoc Kamalkant Chandrakar. So I'll go ahead and share my screen with just a couple of slides here on some background material, just to set the stage. Hopefully this will actually work. Can people see that? Okay, good. All right, so one of the main challenges here is just the huge range of scales that we have to deal with in representing clouds and models. And the particular challenge really depends on the particular type of model. So, this diagram basically represents the kind of full range of atmospheric modeling that we have. Everything from process level modeling with direct numerical simulation. I'm not sure if people can see my cursor here, but on the left here, with small scale models that basically represent individual cloud and precipitation particles and the full range of scales of motion of a turbulent cloud. And then going to larger scales, we can't represent every individual particle just because of the sheer numbers. So going to the right to larger scale models like large eddy simulation, you have to parameterize the microphysics because you can't represent all the particles, but you still resolve most of the important range of scales of motion. So the large eddies and cloud scale motions. And as you go to the further and further right, you have to parameterize more and more of the clouds and cloud scale motions in addition to the microphysics. So out here in the upper right with traditional global climate models with a scale, say, of 100 kilometers, then you really have parameterized microphysics inside parameterized clouds where most of the range of scale of motion with the clouds has to be parameterized. So it's been referred to as a parameterization squared kind of problem. So with clouds, it's really a twofold problem. there's the kind of, you call it, I guess, the traditional or classical parameterization problem of how to parameterize unresolved scales, depending on the type of model, like I just showed on the last slide. And then somewhat distinct from that, uncertainty in the fundamental physical processes. So because of the latter, even at the scale of individual cloud and precipitation particles, say in a DNS model, there's still large uncertainties in our understanding of the underlying microphysics. So that there's incomplete theory with significant knowledge gaps and no complete benchmark model. So in a lot of ways, this is fundamentally different from other aspects like radiation, where at least for clear sky, we have line-by-line models that can provide a good benchmark, or fluid dynamics turbulence, where of course Navier-Stokes equations describe flow very well for atmospheric conditions. So as a result of this kind of fundamental process uncertainty, even in very simple modeling frameworks, there can be a pretty substantial spread of model results. That's illustrated in some work from Olivier Pratt that we published a few years ago. And this shows using different state-of-the-art drop, collision, and breakup kernels, just in a simple 1D rainshaft model where you specify a raindrop size distribution at the model top and just let that fall and achieve steady state. So the different colors here represent different kernels, and you can see a pretty large spread once it achieves steady state after 60 minutes. The one in the middle right here shows a spread of drop concentration by about a factor of 2. Keep in mind, this is a log scale down here. Again, I'm assuming people can see my cursor. And then if you go on the right here, the median drop diameter has a spread of about 25%. So it's pretty substantial uncertainty just from that one process associated with drop breakup and coalescence. And of course, for ice microphysics, there are even arguably larger uncertainties at the kind of fundamental level. So this kind of uncertainty is manifest by the large spread of model results using different microphysics schemes. And one thing I want to emphasize here is that increasing scheme complexity, say going from bulk schemes to bin schemes, has not necessarily resulted in a reduction of that spread or a convergence. This is illustrated from some work by Lulin and others a few years back. And it basically shows some quasi-idealized squall line simulations using the WRF model and 3 different bin schemes here in the left and 4 different bulk schemes in the middle. And you can see here that the spread of these state-of-the-art bin schemes is just as large or perhaps even larger than the bulk schemes. For example, you quantify that by, the spread of the location of the leading edge of the storm, for example. And these differences are robust and not a result of just different flow realizations, which you can see here in the right panel, where we generate different flow realizations just by adding very small perturbations to the initial conditions with one of the schemes here. And those differences are much smaller, obviously. So of course, observations are really a key because we have this limited theoretical knowledge of many microphysical processes. So we really need empirical constraint from observations. And we now have a wealth of cloud and precipitation observations for constraining schemes from a variety of different platforms. Of course, a large part of ICCP is we've heard a lot of talks devoted to that. A key question is how to actually use these observations, though, to constrain schemes rigorously. This is actually quite challenging because we generally cannot measure the microphysical process rates directly, at least on an individual level, but their net effects on cloud and precipitation. So you measure some kind of cloud and precipitation properties that are the result of some integrated effect of the microphysical processes. So in effect, these provide an emergent constraint, but not direct constraint of schemes, with some exceptions. For example, there's a history going back several decades of using observations of particle size distributions within bulk schemes. And as more complex schemes are developed, this arguably makes constraint with observations even more difficult. So this is the last slide. And these are some themes that we came up with for model improvement. And I don't think we're going to discuss all of these here, but I just wanted to put this up as a way to maybe jumpstart the discussion, and I can leave it up. I'll very briefly just go through this. The first, the development of new detailed process level models, particularly Lagrangian particle-based schemes. There's talks on this at ICCP, and there was quite a bit of discussion on this at the cloud modeling workshop last week. A more rigorous constraint of parameterizations using cloud and precipitation observations or detailed process models. So incorporating, some elements from statistics, trying to constrain schemes more rigorously. Improvements via laboratory studies, which is, again, another important component of work being presented at ICCP, where we can really isolate processes more so than, bulk cloud and precipitation observations. Incorporating machine learning, artificial intelligence, stochastic cloud and microphysics schemes, improved subgrid scale dynamical schemes and coupling with microphysics, again, relevant basically across all scales of models from LES to large scale client models. And then improved cloud and microphysics for data assimilation, like Axel mentioned. And I will end there. And just leave that up. And then, like I said, we kind of just keep it open for discussion. I'm not sure if there are some audience questions to start off with. Okay, there's one request here. I request everyone not to block the doorway. Okay, that's good. So please, type questions into chat for people who might have them, and then the panel can address those. And I'm not sure if people can raise hands or whatever. I'm not sure if that feature is here to come up and actually ask a question in person. The moderators, I guess, can illustrate that. Okay, I see one hand raised from Lulin. So there is.
Yeah.
Okay, there it is on the right. So if we don't have any particular questions, I think we can just kind of go ahead and start the discussion. Maybe I can put a couple of people on the spot here. Axel, I thought your take on the importance of advances in models related to the data assimilation problem was a good addition to this. Do you want to maybe quick say a bit more about that and sort of where you see that topic going?
I think it's just something that's happening now or in recent years at weather services, that we are more and more trying to make use also of cloud observations, especially cloudy pixels of satellite observations. And this really requires to get better constraints on clouds in model, or this gives us some constraints, and we have to improve our representation of clouds. So over many years, it was actually not so important how the clouds looked like as soon as the precipitation was okay from a application point of view. But this really changes now with the assimilation of cloudy observations. So we have to get the clouds right. Otherwise, we will not be able to use these observations. And what this changes, for example, in our department, is that we have to talk much more to the data assimilation people and explain them where the biases are and which of them we can fix or not. So there's a lot of going on, and I think it really pushes the cloud modeling to actually get things improved.
Okay. How does incorporating more detailed schemes, like two-moment schemes, play into that? Because I'm assuming that that can introduce some additional challenges in and how you basically assimilate observations into that more detailed framework.
Yeah, yes, of course, we hope that this helps, but it's also a challenge, because then you have to treat all these details also in your radiation scheme. So you have to pass the effective radius to the radiation. You have to treat snowflakes in radiation. So that's what I mean. We have to talk a lot more across different areas of the model. So radiation people have to talk with cloud people, and all of them have to talk with the observationalists, which are basically the data assimilation people, to interact. Is this really an improvement? Is this going in the right direction? And so I still think the treatment of larger ice particles in radiation is still a challenge, for example.
Okay. Good. I see a few people have come up to the stage, so I'll sort of hand this off, I guess. I see George there. We also have a question in chat, but maybe, George, I don't know if you want to have a comment first.
Yeah, you're referring to me?
Yes.
Yeah, my main comment is that we don't know how well our predictions of clouds and precipitation are doing now quantitatively. So both from the weather forecasting and the climate point of view. So I think our first priority is to find out how well we're doing now, so that we can benchmark what it is like now, and we can say, does this improve? Does a triple moment scheme improve, or whatever? So I think that's absolutely vital. I know from my own ad hoc comparisons of observations with models that models aren't doing a very good job of predicting cloud occurrence or precipitation amounts.
Mm-hmm. Yeah, and one challenge I think in that, to generalize it, is of course it depends on what application you're in, what you really care about, and in a comparison, what you want the model to perform at. Obviously for climate, you have different constraints than a weather model. But yeah, I think, your point is really well taken. We need to sort of know where we stand on things relative to how well they do in a practical sense compared to observations.
Well, I made a point in one of the other panel discussions that a 2 or 3% change in cloud cover can offset global warming, but we don't know where we stand right now.
Mm-hmm. I see a few hands up. I can't see. I think it's Lulin and Paul.
Right.
Lulin, go ahead.
Yeah. First, I would like to just ask everybody, if you have questions, you're able to raise your hand. So use the icon, emoji icon at the bottom of your screen. You're able to raise your hand, and then Tara Harish can spotlight you, so you can ask your questions in your seat. You don't have to come up to the red seat to be heard. So that's kind of a more logistic comments here. But then I will save my more detailed kind of elaboration on other aspects later. I will ask Paul to follow his comments.
Okay, I was just going to respond a bit to what George was saying. So, I would have thought lots of operational weather centers have verification systems, so you can compare, hundreds of cases against synoptic observations. Ideally, but the frustrating thing at the moment for us is that it tends to be what's observed at 1 meter or 1.5 meters when we do have observations throughout the whole atmosphere. So it'd be nice to include those. You do try to include a whole basket of predictions or forecasts that are important to a range of different people. The other problem is, though, that having such critical assessment cuts both ways. So you could change your model or change your microphysics representation so it's the best representation of all the physics out there we know of at the process level. But if that doesn't play well with your boundary layer scheme for mixing, or your cloud fraction scheme, or your radiation scheme, then you could make the overall performance of the model worse. And so it's a big uphill struggle then to get your improved physics into the final model, because you have to improve everything else as well around it. So it gets tougher and tougher.
Thanks, Paul. There are some questions coming in the chat. Maybe we can go to those, unless someone has a follow-up on that last point.
Dr. Hykevix, you're spotlighted. You can speak.
I don't know. Can you hear me? And should I speak now?
Yes.
Yes. Go ahead.
Fantastic. Yeah, actually, I mean, I wrote my question while Alex was talking, and now Paul also kind of referred to it, probably without knowing it. So my question is, if we do have general goals, so I think the introduction now seems to imply a little bit like we would have that one, in German it would be eierlegende Wollmilchsau, like something that can solve everything. And I don't think that this exists, or if it would exist, I mean, what are our goals? What do we want to learn from the modeling? And I think this probably has to be asked first before we try to put everything together and make it too complicated. Or maybe there are common goals. That's my question. I mean, what do you see as the main goals that should be reached with using the models?
Maybe I can just comment on that. So I think most of the big model development centers are developing kind of general purpose models, which can be used as global climate or NWP models down to really regional models. And we have to specify and formulate the microphysics and the cloud physics for that. So this is a very broad problem and topic. And I think we are doing actually pretty good on that. And I would, on some level, disagree with George. The models have improved in the last years tremendously, and in many of the variables, you cannot easily distinguish observations from models. For example, I can give you a satellite image, and you would not be able to distinguish the model from the observations. I completely agree that we have still issues like with mixed phase clouds and subcooled liquid water, and you know all this. But in general, we are pretty good in solving this really broad problem. And I'm pretty sure Paul would agree with that.
Okay. I think Paul has his hand up.
No, that's fine. I just carry on. Somebody else can talk.
I was just going to say that I think there are multiple goals, though. I mean, certainly accurate weather forecasting and climate forecasting is a goal, but I think there's also a more general goal of just to understand our observations and understand the physical processes going on in the atmosphere. And I think that's where some of the more detailed models like the Lagrangian particle schemes or bin schemes maybe play more of a role is just fundamentally understanding these processes that we still struggle to explain.
Yeah, I think that's a good point. I mean, I would hope that our general goal is to get realistic physics into models, regardless of what those models are, a climate model, a weather model, whatever. I know that's a very broad statement, and in practice, that's not necessarily top priority in, say, in an operational weather model. You know, I think Jason could probably comment a bit more on that point too. But, you know, that is, I think, a general goal of where I see sort of things going with model improvement is you want to improve the basic underlying knowledge of the physics and get that into models across all scales.
Yeah, I think I'll second Adele's comment. I believe, indeed, we want to have like a two-stream kind of approach. And when we have the bottom line kind of a fundamental understanding, more benchmark understanding of the microphysics. And then as Hugh showed, we have a parameterization square problem. So then we have to understand the basis and then carry on and upscale those understanding to a further larger scale models. And I think we would like to address some of our audience question. I saw Ismail has the hand up, so we should let her speak.
Professor Ismail is already spotlighted. You may speak.
Yeah, unmute yourself.
Yeah, we can't hear you, Ishmael.
No, we can't. I saw Graham Feingold's hands up. Maybe we move to Graham first and see if Ishmael can come back with unmuted. Graham?
Yes. So to Adele's point, I think there's a very good development in recent years, which is the routine LES modeling alongside routine observations. And it's putting LES through the paces much like NWP is put through the paces on a regular basis. Of course, you don't have the public yelling and shouting when you get the LES simulations wrong. But it really gives you an opportunity to not just do case studies, but to run many cases fairly routinely. Of course, it depends on your interest in the location of these test beds. And I think that's proving really, really valuable.
There are a few comments that have come in as well here in the chat. Weinman Gong said, cloud modeling needs differ for different communities and applications. For NWP, the focus may be on precipitation and severe weather events. For climate, rate of properties are important. For air quality applications, cloud optical properties and precipitation are important. I guess that's a comment more as a question. And yeah, I agree with that. Peter Breckner asked, what are the biggest biases in commonly used parameterizations? That's a good question. I think it's pretty tough to answer that because it depends so much on the application of what, schemes are used now across different models, different applications. I can maybe speak to a few of them. I think Axel had touched on mixed phase clouds being problematic in many models of different scales. There's also, I still think there's some issues with warm rain generation, particularly in bulk schemes, the auto-conversion process. I think there's some people on the panel that can probably speak more to that issue as well, if we want to talk about that. But I think there are a few kind of common biases that, can be targeted or, are present across different models. I don't know if other people have other opinions on that or some follow-up on that. Yep, Jason? I think you're muted.
Yeah, hi. No, I was going to, I wasn't going to talk about that. I was going to follow up. I was going to say something else. Can I proceed?
Yeah.
Okay. Yeah, I was going to make a sort of responding to a few different comments. First, I wanted to maybe just mention something I really should have, I was going to do yesterday in the instrument and measurement discussion. Somebody had pointed out that modelers would benefit a lot from spending a day in an aircraft looking at real observations and getting a sense of the complexity of the observation world, and I think that's completely true. Andrea Flossman then sort of retorted that the observationalists should similarly spend a day with the modelers to understand some of the complexity of the models. And I privately said here, because I didn't want to look like a grumpy modeler, but she encouraged me later that, no, I would have appreciated some public support on that. And so anyway, so there's your public support. And I think both are true. And back to the whole verification thing, and I think George's point is bang on. If we don't understand whether or not, if we don't have a good sense of verification, we don't really know if we're going in the right direction or not. And I think that there is a lot of, it's sort of all over the map what modelers do in terms of verification. And some make good use of observations and some don't fully understand the observations. I don't know how many papers I've reviewed in which they make direct comparisons to radar reflectivity to the model reflectivity and so forth, without understanding slight errors in bulk schemes and so forth. Anyway, I'm rambling a bit, but the Andrew Gettleman had this great analogy of a numerical model in the physics of an atmospheric model of sled dogs, in which each dog in the sled is a physics parameterization, and the modeler is the sled dog master, and every dog is a bit different. You got to balance them in order to get the sled to go straight. And as soon as you remove one of the dogs and put in a much stronger dog, the analogy being to a better and more physical parameterization scheme, it actually screws up the forecast, because now the things are out of whack. And so in the NWP community, and I think this is what Paul said, is that at the end of the day, we all want the better physics, but it's the end result, the operational forecast, counts for next year's implementation. On the flip side, last week at the cloud modeling workshop, somebody had told me, I think it was Hugh, that if I mentioned NWP there, I'll get blacklisted from that workshop. That was a bit of a joke, but I think there's a lot of truth behind that. I think that workshop focuses sort of on the real cool cloud modeling, the state of the art, trying to get at the physics, better physical processes and realistic modeling. And I think the point I'm trying to make is that I think those two sort of schools of thought, the cutting edge cloud modeling, and then the operational NWP, cloud microphysics schemes for NWP, are there's a bit of they're not on the same wavelength, and I think that the modeling community as a whole would benefit if we got synced a little bit better with that. If that first slide that Hugh showed with the different modeling, the different scales and so forth, is already soon to be outdated. The global models are going to be at 1 kilometer in a few years, and operational NWP models are going to be at sub-kilometer scale. So we're very quickly approaching, in operational NWP, the state where the microphysics schemes, which are playing an increasingly important role, are of the same caliber that we were talking about in the cloud modeling workshop a few years ago. So, well, if I haven't made my implicit point already, I guess maybe I could just shut up and let people respond. But I guess my request is that I think in the cloud physics community, I think we need to include the NWP people a bit more. Now, of course, Paul, Axel, and I are all on the panel, so maybe that is going to be sort of the empirical proof that everybody's already included. But another point about that is it is the modeling experts that have a better understanding, I think, of how to better exploit a lot of the microphysics information that's in the model that can be used for high impact weather. Right now, the weather centers, we're so stuck with these traditional metrics. We have to put in a double moment scheme and then prove that the 500 millibar heights are better. Whereas we don't look at how that improves the parameterization of lightning or aircraft icing potential, or other high impact weather elements that the microphysics schemes can exploit. So I propose a more conscientious inclusion of the sort of the cutting edge cloud modelers with the NWP modelers.
Okay, thanks. Let's go with Corinna and then Paul after.
Yeah, thanks. I actually wanted to add something to the first point that you made, Jason, on that modelers should spend time in the field. I would like to add that modelers should also spend time in the lab, or at least discuss with people who make laboratory experiments on cloud physics more, because very often our parameterizations are based on some laboratory experiments, and I often have the feeling that there's limited understanding of how they are derived and what the limitations are. So, and in particular, I think at the moment there's really a lot of exciting new experiments under development. I'm again thinking of ice formation processes here, both secondary and primary. There's a wealth of information that we need to digest and derive suitable parameterizations for our models. And that's not an easy task, and I think it can only be achieved in close collaboration. So another call here for more interaction within the entire cloud physics community.
Agreed. I think Paul is next.
Yeah, I was just going to respond specifically to what Peter raised about biggest biases. So if I wanted something tomorrow that would improve things or help me, would be to have some way of understanding how to deal with mixed phase overlap or any species overlap in a grid box. Because we have all of our, so if you take mixed phase, say, we have all our understanding of all the process rates like rhyming or diffusional growth. And we have so much water in a grid box and so much ice. But if we don't know how much they're overlapped, our process rates for the mixed phase processes could be out by very large factors of 100. So I've seen some talks this week where it looks like we could get some empirical understanding of what that mixed phase overlap should be as some kind of environmental parameters. But it'd be nice to get some theoretical understanding as well, so that we're not just slave to some empirical relations. So that's my biggest bias, I think, that is I can just set this overlap fraction to whatever I want to get whatever I want from the model. So it'd be nice to have some at least observational backup, and then theoretical would be ideal.
Go ahead, Lulin.
Okay, I really appreciate Karina's point that the lab component is very important to our modeler as well, especially those detailed quantitative parameterization and the process rates. And today our topic is how can we improve clouds in models. I kind of understand this topic. It has like a two-prong or two components. One is what type of methodology or concept that we can use or develop based on the physics and also observation. And the other side, in my opinion, is what Jason has raised, is how we can actually crosstalk or collaborate with each other more closely to bridge some of these informations that the other side may not be quite familiar with. So in last week, we have our International Cloud Modeling Workshop, and it was the first time that we actually have a case that simulated a lab condition, the pi chamber experiment. So it was a very nice, I would say, a experiment that tried to link the very fundamental physics with the control environment of a lab setup and lab results. And by conducting this into comparison, we learned so many more details about how observations are collected and what the uncertainties associated with the environment, and at the same time, what amazing physics that we ignore or forget about in the models. I strongly support the idea that either ICCP or some consortium type of organization there to facilitate more of these collaborations between modelers and observationalists, and also including the operational numerical forecast community, to really identify those trivial information that's not being paid attention to but important to the question. So that's kind of my thoughts thrown on the stage.
I think maybe before you go, Axel, because there's a very pertinent comment to this from Greg McFarquhar that I can quick read here. One activity of the upcoming commission will be to sponsor workshops before or after other conferences on topics where we can reasonably expect to make progress with some focused discussions. What would be a couple of focus topics that might be good to focus on for a first model observational workshop? It would be interesting to hear some comments from the panel members on this. So this is kind of along this theme. So maybe let that marinate for a few minutes, and then we'll go to Axel next.
Okay, so it's me now. I just wanted to make the connection between something that Adele said about process level and Lagrangian particle methods and the need to go to the lab, because I think these two things work very nicely together. And in my opinion, for the next decade, I expect most of the progress in cloud modeling work from these Lagrangian particle methods. And also because by putting those together, you are really forced to go back to the basic microphysical questions about what is the terminal fall velocity of a rhymed particle as a function of degree of rhyming, or how does the fall speed depend on the particle habit, and this in a continuous way. So if you do this Lagrangian particle approach, which is, I think, a very natural way of doing cloud microphysics, you really have to go back to the very details of the particle description. And of course, to get this data, you have to go to the lab people, or we have to get new lab experiments. So I would actually hope that this emergence of the Lagrangian particle methods also gives the whole community kind of a new boost, a new kind of motivation to go back to these fundamental questions. And I would hope that especially young people would pick up these opportunities to use these new methods.
Go ahead, Adele.
Yes, yeah. So I agree with your comments, Axel, and I think one of the things that makes Lagrangian particle schemes exciting is that they're a relatively new and innovative way to approach the microphysics modeling problem, and I think that potentially bulk schemes could also benefit from some innovative thinking as well. With Jason and Hugh's P3 scheme, taking a totally new approach to ice, and we've seen that be very successful. And so I also wonder sometimes if we need to think more about new ways to approach the bulk modeling problems.
One thing too that we can maybe think about along these lines, as well as with Greg's comment on the focused workshop and kind of observational model topic, is start thinking of ways to really think about how these, I think, really exciting advances in process level models, specifically Lagrangian particle-based schemes, can inform bulk schemes and models for larger scale models. I know you've done some work on that, Axel, in your 2019 James paper, using a particle-based model as a benchmark. But I think it's good to think about how that could be done, in a systematic way, or in maybe a broader effort to really use these emerging methods in that way. But I totally agree with what you're saying, Axel. In the next 10, however many years, I really see Lagrangian microphysics schemes is taking off. I mean, even in the last few years, they've really been taking off, and I'm excited about more schemes being developed, particularly on the ice side of things in the mixed phase. I'm not sure if there's too many right now. I know there's Shima's mixed phase scheme that he's working on, and then yours, Axel, but I'm not, mixed snow, but I'm not sure if there's many really beyond that yet. So I'm hoping that there's gonna be a push in that direction, and eventually intercomparisons and so forth among those schemes. Because like you said, that really gets back to the basic physics. You have to know something about details of the ice particles to really do that in a physical way, and it really motivates that.
I think Paul Connolly have his hand up for a while.
Yeah, we'll go to Paul next. Is he spotlighted?
Yes.
Hi, can you hear me?
Yes.
Good. Yeah, just talking about bulk microphysics. We've talked about double moment, and I think some people said for NWP that can cause problems too. So like double moment, you're storing the number and the mass, but also the shape parameter of the size distributions can be important. This parameter, if it's positive, it means there are going to be more large particles, and if it's negative, there are going to be more smaller particles, and that can impact things like the growth rates of the particles and the fall speeds, which can impact on the forecast. I think maybe there's a role for in situ measurements to improve the description of the shape parameter. So by looking at more state-of-the-art in situ observations of the size distribution, maybe we can look to see if there are any systematic variations with temperature or in different locations to see how the shape parameter varies with, say, ice water content or ice crystal number. Another example, the shape parameter, because it affects how many small particles are assumed in the size distribution and large particles. When you start to look at secondary ice processes, which might involve collisions between droplets and ice crystals or ice crystals too, that's another place where the shape parameter can have a big effect. So depending what the shape parameter is, that determines how broad the size distribution is, which will determine how many collisions there are between the ice crystals. So, yeah.
Okay, thank you.
So so the role of in situ measurements, I think, could play a role there.
Mm-hmm. There's a question from Sue Vandenhever on the role of satellite observations. So there's a newly proposed NASA mission, formerly referred to as ACCP, which is focused on aerosol cloud convection precipitation. The currently proposed mission will have both a polar orbit and an inclined orbit and will include a suite of different measurements. What does the panel feel will be the most useful observations from space that will assist in enhancing our microphysical representations? Any takers on that one? Yeah, go ahead, Paul.
I'll say ice water path, ice water content, anything like that. We have decent liquid water measurements, microwave over ocean at least, so it'd be nice to have similarly accurate or quality ice water measurements too.
Well, and you had mentioned, Paul, too, about some of the overlap assumptions and, subgrid scale, subgrid and larger scale models, subgrid scale distributions. And if you assume different parameterizations for that, you can sort of get anything you want. So I would think that would also be a really kind of key thing to try and nail down a bit more too from satellite measurements. I think Axel had his hand. You might have lost your connection there for a second. I saw you have your hand up and then you disappeared. But I think you're back. Okay.
Now I'm back, maybe, but yeah, it's probably too late to change any NASA mission and specification of satellites. But as I mentioned in the introduction, I'm pretty excited about active remote sensing techniques that have been really improving in the last years, especially multi-frequency and spectrally resolved polarimetry. So polarimetry is a function of Doppler velocity, or when you combine all this with Doppler velocity, you get kind of a spectrally resolved information. And that was really an eye-opener for me, how to use this active remote sensing. For example, with polarimetry, I was always confused about these quantities. And if you start decomposing them spectrally or by size or by fall velocity, basically, it starts to make a lot more sense to me and contains a lot more information. So if we could get something like that from space, that would, of course, be amazing. But I think these advanced radar technologies are too new to put on a satellite. But I can just kind of say that I think this, for model validation or for understanding even microphysical processes, is really a great tool.
Okay. I don't see any hands up right now. We can go back and there's another comment in the chat related to difficulty of determining ice physical properties, mass size relations. And specifically here, I'm thinking about mass size relations and observations. It is not easy to differentiate the distribution of pristine ice to aggregates, and it makes it hard to retrieve densities of various types of hydrometeors. So yes, it goes back to, the whole issue of ice particle properties, and the particle properties really being a key. In particular, we care about the densities, at least in my experience, primarily because of the effect on the fall speeds. The fall speed is really the key, and I would love if we could have better observational constraint on ice fall speeds, particularly in conditions where you might have, or you might expect, a wider range of particle fall speeds, like in deep convective clouds where you get ice that can fall, several meters a second. I don't have a sense as to what's missing or what the challenges are, and really trying to nail that down better observationally. I'm sure there's many others here that can comment on that more, but it's just something I want to throw out there. Okay.
Yeah, Graham has his hand up.
Okay, I can't see that, but I'll take your word for it.
Hugh, apologies. I'll go back to something that Axel said, which I think is interesting and important. And this came up in yesterday's discussion on the observational side. I think that the remote sensing provides really strong constraints, particularly when you take multiple geophysical variables. So, if you've got radar plus, some sort of spectrometer giving you optical depth, the two can be really useful for interpreting processes, and Kenta Suzuki has done a lot of work on this. And as you start adding other geophysical variables, not necessarily just two at a time, you really start getting a much better idea of the behavior of your model compared to the observations. But more importantly, if you choose your geophysical variables carefully, you can actually get some understanding of the physical processes. And that link between the evolution or the behavior of these geophysical variables and the processes is really key for improving models. So I'd like to just raise that point again and see if the panel has any thoughts on that.
Yeah, Paul, go ahead.
Well, I was just going to, when you do, typically, I guess climate models, they tend to compare lots of different fields, so radiation, microwave, winds, aloft and near the surface. So is that the sort of thing you have in mind? I mean, ideally, it's less. The three-dimensional nature of those comparisons are done less at NWP. They tend to be more focused on surface, where most customers are interested. But for things like global, obviously, aircraft people are interested in winds and so on. Is that the sort of thing? I mean, so there's when you do a climate model, you'll be comparing against all of those geophysical parameters, radiation, every observation from satellite can give you.
Paul, the key to what I'm saying is not the multiple number of geophysical variables that you compare against, but comparing them in a joint PDF sense. So if you compare radar reflectivity, if you take radar reflectivity on one axis and optical depth on another, and you look at the behavior of your model output or your observations, you will be able to detect coalescence growth, for example, versus condensation growth. It's just a simple example of what I mean. But I think as you tie in more of these geophysical variables, you can simultaneously, so I'm thinking now in a joint sense, tie down your processes way better than looking at each one of these independently. So that's, I think, key to what I'm getting at.
Yeah, I'd agree.
Yeah, and it gets back to the whole, we can't really measure processes directly very well outside of a lab. But if you can cleverly combine different observational information, you can maybe begin to get at that. I think that's basically what you're saying, right, Graham? Particularly, I think you gave the examples from warm rain processes, which, I'll still contend that we still struggle with that in bulk schemes, getting that correctly. So yeah, I totally support better use of constraint like that with multiple quantities and clever ways to try and tease that out. So let's go with Lulin and then Axel.
Yeah, I want to just echo actually Graham's point, address one of our questions in the chat that Tara raised. So Tara asked, what should be the strategy for model evaluations to see if the microphysics is correct? And it kind of, as a way that Graham just illustrated, is one of the kind of the way we can adapt to evaluate model. At the same time, we do need kind of a multiple level and scales of observations to help us understand whether the simulated cloud is right or not. Even for a very specific time constraint and geophysically limited region, if you want to really evaluate whether you get the right clouds and right phenomena or not, we would like to have as detailed observations as possible to evaluate the whole simulation. So that's probably more like a targeted field campaign can address. But how to generalize that into a more strategy type of question, I don't have the answer, but just throw that comments out.
Maybe getting back to Greg's comment earlier, maybe a workshop on how to understand processes like this from joint observations would be a good topic.
Axel, did you still have a follow-up on that, or?
Maybe just rephrasing Graham's ideas again. I think Alan Betts some years ago called this that we should validate relations between variables and not trying to compare variable from a model with the variable in the observations, but find meaningful physically based relations between variables that we can then basically plot or analyze from the observations and also from the models and compare on that level. And this, I think, gives you a much more robust understanding and a better insight into the behavior on a hopefully process level. And this is also something that kind of observationalists can try to bring forward when they have a good observational data sets. They can try to find these relations between their observations or between their variables and then challenge the modelers to show, has the model the same behavior, the same relation? And I think that's a good approach to bring observationalists and modelers together without doing this point-by-point exercise.
Mm-hmm. All right. Well, are there further comments? We're about 4 minutes past now, so I think we can wrap things up. Lulin, you have your hand raised.
No, thumbs up. But yeah, Wojtek is not here, but I think he would like to express his support to Lagrangian-based microphysics and mixed-phase microphysics in the future. So I think Hugh and Axel touch base on that, and just want to bring his opinion on the table.
Okay. So Jason suggested that at the end, each of us say what we think is the most pressing issue in modeling. We can maybe put people on the spot a little bit here, and then I think we should end things at that point since we're running a bit over. Any comments? Jason, maybe you should start since you're the one.
I suppose that's only fair. Yeah, I guess my question was, the topic of panel discussion was a question, how to improve clouds and models. And there's modeling techniques, observational techniques, etc. I think the most pressing question or whatever that should be done sort of is the most urgent for this to answer this question is to how Tara put it, is to establish an agreed upon strategy for model evaluation. And that can be fine-tuned and adjusted over the years. But I think that without that, the model evaluation is very all over the place.
Okay. Related to this, there is a comment, I think, by CC Chen that I definitely echo as well, and something that I hope observationalists can consider more as well, but it's getting a relative humidity or supersaturation, which is, of course, notoriously hard to derive from observations, and is really, a key from the standpoint of microphysical processes and warm rain processes. So I already sort of gave mine. I think getting, constraining ice fall speeds is really critical. I don't know if that's the most pressing issue, but I think it's certainly from the standpoint of constraining with observations, I'd love to see ice fall speeds constrained more. Like I said, that's really why we care a lot about particle habit, densities and so forth. Of course, it affects the radiation as well with the particle habit in a direct way, but the fall speed is really a key for that. I don't know if any other panelists sort of have a pet topic or issue that they would like to see better constrained in models, or a pressing issue. If not, I think we can maybe wrap things up here.
Oh, we haven't discussed secondary ice. I would just say it is important and we care about it, although we didn't discuss it in this discussion now. And I know I'm also supporting the supersaturation over liquid. That's really an issue. We heard today this really nice talk by Bill Cotton about condensational invigoration, and this is in the end very much about constraining supersaturation.
A quick mention in the chat. So Corinna did mention as an answer to Greg's question, one of maybe a focused topical workshop on secondary ice production, which I think a lot of us would support something like that, since it's a topic of high interest right now and really important in the models. It just came up in the chat and not in the discussion itself. Sorry, Lulin, go ahead.
I just want to say, even though we are really interested in secondary ice formation, but I still want to put forward that primary ice nucleation and formation is still a unsolved problem. So we still want to know where the first ice formed, and then second ice will probably start. So that's also important microphysical issues that we should address hard. So that's my kind of a final comment.
Okay, great. Final comments before we wrap up? Going once? Going twice? All right. Well, thanks a lot to the panelists, and thanks for the audience questions and for the participation. And I think we can wrap things up here.
Thank you, Hugh. And there are some hand raised. I think there are some people wanting to say some comments.
Okay, sorry. I actually can't see in my window here people's hands raised. So.
Please come forward to the red sofas and please speak up. Yeah, I don't see any hand raised right now, but there are Stephen, do you want to speak? Yeah, I don't see any hand raised now. There are no further comments. Yeah, okay. There is one comment from Fred Brechel. I would like to echo the recommendations to better connect observations and modelers. Perhaps ICP could create a match.com construct So PIs can connect across knowledge areas. Modelers can and should help direct measurement campaigns. Observationals need to explain measurement limitations and adapt capabilities to satisfy model development needs.
Yes, thanks for that comment. I think we all would agree with that. So it's a matter of sort of how to make that happen in practice. In my experience, it works basically from the grassroots level up. Like you sit down and chat amongst each other in a small group, or even one-on-one, and it builds up from there. So I hope the observationalists please come and offline or after this or whatever, come and engage us as modelers. We like those kind of discussions, and I really think that's the way it has to happen to get it to work. All right.
Yeah. Thank you. Thank you, everyone.
Okay.
Thank you.
Yep.
Thank you, everyone.
Okay.
See
Bye-bye.
you tomorrow.
Bye.
Thank you.